The next 4 weeks then, we will have Peter Kravchuk from King's, and he will be telling us things about CFTs in Lorentzian signature.
All right. Thank you for the introduction. So, hello everyone. It's my first time here. It's a very nice room. I'll try to figure out how to use this Blackboard. So, the topic of this lectures is going to be, it's called CFTs in Lorentzian signature, but it's going to be about conformal field theory, maybe some aspects which aren't usually in textbooks, and so I hope you'll be able to learn something new. That said, I know that there are people in this audience who know far too much about it, so I apologize in advance for being too basic. Of course, if you have any questions, please interrupt me, and I will place carefully designed intentional mistakes in everything that I say, and so it's your job to catch that, and it's going to be only intentional mistakes. All right, so let's start. First, let me just say a couple of words of introduction. Maybe let's first ask, so who attended Andy Sturgis lectures? Can you raise your hand just so that I get an idea? All right. Who have worked with or learned conformal field theory before in more than 2 dimensions? Okay. So this should probably stress that I have no idea, generally speaking, where you are at. So if something that is unclear, stop me and ask. If I'm being too basic, then start booing, and we'll somehow adjust. So this is going to be about conformal field theory. And conformal field theory has a bunch of applications, and if you read how people usually motivate it, there are a few themes which usually recurring. So one is very sort of down-to-earth critical phenomena. So this is the idea of studying phase transitions, continuous phase transitions in various contexts, in kind of experimentally relevant setups. And at critical points, various systems can exhibit scale invariance, which in the end often can be described by conformal field theory. Oops. Another application, and probably Andy, if I had to guess, talked more about this in his lectures. Another application is just general to quantum field theory. And this is in the context of, one simple idea is that, of course, conformal field theory is just a special case of quantum field theory. So if you want to understand something about quantum field theories, you might start with a special case, which is conformal field theory, which is simpler. But also you can view, a common theme is that you can view quantum field theories as RG flows between conformal field theories in the UV and in the IR. And so the whole RG flow you understand as a quantum field theory. And so in this way you can view general quantum field theories, not all of them, but general quantum field theories as, say, relevant perturbations of conformal field theories. And that's another application. And then yet another application, which is sort of popular among people who like gravity, is to ideas CFT. So there is a duality between quantum gravity in anti-de Sitter space-time and conformal field theory and its boundary. And so, if you want to learn about quantum field theory using quantum gravity using ideas CFT, it's a good idea to learn about conformal field theory. Then there are, some people might say that there is DS CFT. This is a bit less established, and then there are many other more speculative applications. And so somehow, I think if you open most texts, modern texts on lecture notes on conformal field theory, you'll be able to learn conformal field theory, but mostly it's going to be conformal field theory in Euclidean signature. You'll learn things like radial quantization, conformal block expansion, conformal bootstrap. But almost universally, this is studied in Euclidean signature. And in principle, this has good reasons. One practical reason is that studying quantum field theories in general in Euclidean signature is just simpler. Some things are tidier, more things are positive. It's a bit easier there are fewer singularities, it's a bit easier to technically just work with them. Another reason is, for example, if you want to understand critical phenomena, then many of them require you to work on, many applications here would require you to work on in Euclidean signature. For example, if you study so-called classical phase transitions, something that Andy talked about for sure, this is where you would apply Euclidean version of a conformal field theory. That said, all these applications, they also have an important Lorentzian side. And so even in critical phenomena, there are phase transitions known as quantum phase transitions, in which case you are studying real-time dynamics. The difference between Euclidean and Lorentzian is, roughly speaking, that Euclidean studies some kind of statistical properties, and Lorentzian signature, you study real-time dynamics, how things evolve in time. And although a lot of phase transitions have the statistical nature to them, there is also a class, which is very wide and important, of quantum phase transitions, which are more like real-time dynamics, Hilbert spaces, and so on. Of course, quantum field theory applications, again, you might study quantum field theory in Euclidean, and then Euclidean CFTs are appropriate for that. But in principle, when people were inventing quantum field theory, they were motivated by studying how things evolve in time. And so there's, of course, real-time quantum field theories are very important. For example, if you want to understand what's going on at LHC, you have to sure use Lorentzian quantum field theory, and so Lorentzian CFT is more relevant in that case. And of course, in ADS CFT, you can study sort of more statistical properties of quantum gravity, like black hole thermodynamics, and then maybe Euclidean CFTs are okay for that. But there are also many interesting dynamical questions like high energy scattering, etc., in ADS, which again you would address using Lorentzian conformal field theory. And so the goal of these lectures is to some extent fill the gap that I feel is there about just understanding how to deal with conformal field theory in real time, how things evolve and so on. Any questions about the motivation? All right, do you feel motivated? What we are going to be looking at overall. So,
can I ask you a question?
Yeah.
So, can we just think that if we study, say, quantum field theory or quantum field theory in Euclidean space-time, and suppose I know how to analytically continue the time, I will be able to derive all the properties in the Lorentzian, or do I have to learn new something in the Lorentzian space-time?
Oh, that's sort of question we're going to try to address. The answer is that in principle, yes. In practice, no. So we'll discuss this analytic continuation, and in theory, it's possible to do, but in practice, when you only have approximate results in Euclidean signature, it's very hard to actually use them in Lorentzian. That's, by the way, one of maybe, so I'm not an expert, but maybe you heard about this muon magnetic moment anomaly that people have been discussing for a little while. Not sure what the current status is, but there is this idea that you can search for new physics by measuring very precisely some quantities. So, for example, measuring an anomalous magnetic moment of electron was one of it's like one of the best predictions of theoretical physics. You can compute it in perturbation theory to very high order, get very high precision, then you can measure it very precisely in an experiment, and then it agrees very remarkably. And so that's a very good test of, say, quantum electrodynamics and other parts of standard model. And then when you study, you can also study the anomalous magnetic moment for muon. People have been measuring that. And when you do this, it turns out that contributions from quantum chromodynamics are more important because muon is heavier. And so to give a prediction, so you can measure it accurately, but to give a theory prediction, you need to understand quantum thermodynamics better. But of course, quantum QCD is non-perturbative, and we cannot just compute the required answer, the required quantity, using perturbation theory. And then the other method that we have is more or less lattice. And the thing that lattice does is that it computes things which are Euclidean in nature, because Euclidean is that deals with statistical aspects, and lattice is basically like a statistical Monte Carlo simulation. So things which are kind of more Euclidean observables are easy to compute in the lattice. But turns out that the thing that you need for this anomaly, magnetic moment, anomalous magnetic moment, is is more Lorentzian observable, and there is kind of different ways of computing it, and there's been some tangents with the experiment, and I'm not sure what the current status is, but there was precisely this problem that it's hard to go from Euclidean calculations to Lorentzian calculations. Okay, any other questions? That was probably an answer which was way too long for what you wanted, but. Okay, so we have 4 lectures. In this lecture, I'm going to review some basics of Euclidean CFT and just some introductory things to make sure that we're all on the same page in technical terms. And then in the second lecture, we'll study Regge limit of correlation functions, which is a good example of a Lorentzian observable, which is hard to compute from Euclidean physics. And we'll see that it requires some new ideas like introduction of complex angular momentum. And then we'll discuss in the third lecture we'll discuss what this complex angular momentum means, what are kind of more physical objects associated to it, and the last lecture will, so hopefully by the end of third lecture we'll develop some kind of theory that we'll discuss applications of in the last lecture. So that's a rough plan. I can give you fancy names, but you can read the abstract if you want fancy names. So let's start with basics of Euclidean CFT. So again, if you are familiar with this, I apologize, but let's just suffer through this. So conformal field theory is a quantum field theory which has conformal symmetry. So I'll make sure I'm not missing anything. And let me first remind you very quickly what conformal symmetry is. So if I'm being very formal, then we can consider some sort of manifold M with a metric G on it. So M is a manifold, G is a Riemann metric. And suppose we have some map phi from M to M. Then we say that, again, very formally, we say that phi is a conformal transformation. So phi is a conformal map. If, when you transform metric using this map, so technically we call this pullback of the metric. If the pullback of the metric is just proportional up to some, so this is just a function. Omega is a real function. It's just proportional to the original metric. So this is a very fancy way of writing it. Let me write it out more explicitly in coordinates. So if our map phi, sends x mu to phi mu of x, then what that equation says is that partial phi mu prime x mu partial phi mu prime partial x nu g mu prime is equal to e to the, so the metric, So everything depends on x. Metric can depend on x. And this is supposed to be equal to 2 omega of x g mu of x. So why do we care about this? What this says is that you aren't preserving the metric, but you're sort of almost preserving it in the sense that the new metric differs just by an overall scale. Well, the scale can depend on change from point to point, but what's important is that locally the angles do not change. You can use the metric g to measure infinitesimal distances, and you can use it to measure angles. And when you measure angles, you don't care about such overall prefactors. Now, when you measure distances, of course, that's important. So the conformal map is not going to preserve distances, it's going to preserve angles. And locally, conformal map will look like a combination of rotations, translations, and dilatations, but globally it can be more complicated. And the reason in the end we care about such conformal transformations is that we want to study quantum field theories, and if quantum field theories are local, well, not all of them are local, but we want to study local quantum field theories. And if you happen to have a quantum field theory which is translation, rotation, and scale invariant, then turns out locality often in local quantum field theories, basically in almost all examples that we know of, with some extra conditions, they also become invariant under conformal transformations. So very often, the scale invariance in addition to standard Poincare invariance will give you invariance under this sort of transformations, and the intuitive reason is that these transformations locally look like scale plus Poincare, and local quantum field theories cannot tell that they actually aren't globally this way. So I'm not going to go through the standard exercise here would be to start manipulating these formulas and to find what the solutions are, which is going to summarize the answer. So if you ask about infinitesimal conformal transformations, so if we set phi mu of x to be x mu, so this would be just the trivial transformation, but if we add a little bit of psi mu of x plus some higher order terms, so think here about psi as being small, so plugging it in there, you can compute the following equation. You can find the following equation for psi. So you take covariant derivative of psi, then you add the same with flipped indices, and the result is purely a trace term. So this is proportional to g mu times something. So if you subtract the trace part from the left-hand side, you're going to get 0. So this coefficient here, in fact, is, you can do the calculation, is just going to be 2 omega divided by the space-time dimension. Now this is similar to equation that you get for isometries. So in equations for isometries, you'll have 0 in the right-hand side. And that equation is called the Killing vector equation. This is a conformal Killing vector equation. And if xi satisfies it, it's called the conformal Killing vector. So if you can find the vector fields which solve this equation, then you can exponentiate them and get conformal transformations. And then you can sit down and try to solve it, for example, in flat space or in various dimensions or in some other manifolds. And then famously in 2 dimensions, they're infinitely the space of solutions is infinitely dimensional. And if space-time dimension, which I'll denote by d, is 3 or higher, then it's finite dimensional. And the dimension is something like d plus 2 times d plus 1 over 2. This is dimension in the flat space. If you consider some crazy random manifold, then of course it doesn't have to have any conformal symmetries. And so in the flat space, this finitely many solutions, what they are translations, rotations, scale transformations, rescalings, and or dilatations, and so-called special conformal transformations. So again, if you aren't very familiar with this, it's not going to be required today, but if you've never seen conformal transformations before, I recommend maybe looking at Andy's lectures. He will probably discuss that in a bit more detail.
Is there a generic statement you can make like that about 1D?
In 1D, any vector field is conformal in this sense. So in 1D, there is also an infinite dimensional space solution. In 1D, it doesn't matter what your manifold is. There is going to be always infinite dimensional. In 2D, you can still consider some, well, in 1D, basically any vector field satisfies this, because anything is trace when the index is just one option. All right, so conformal field theory is then a quantum field theory which, in addition to translations, rotations, has this symmetry under dilatations and under special conformal transformations. So in these lectures, we're going to take a particular view of conformal field theory, which is the common view, where we approach the subjects somewhat axiomatically. So let me introduce this approach. And this axiomatic approach, it basically says, in short, that conformal field theory for us is going to be defined by a set of local operators and their correlation functions. So right now we're just going to discuss briefly what we mean by local operators and what properties their correlation functions have. So again, very schematically, for us, CFT is just going to be some collection of local operators, which I'll denote by letters like O1, O2, and so on. So these are local operators. And in addition to that, the set of all their correlation functions. So expressions which I'll denote by this sort of notation. And these are going to be the correlation functions. Now, what's a local operator? Well, a local operator is an expression which, so if I write this a bit more precisely, it's going to be some O, which depends on space-time position. So X here is an element of our space-time, which is going to be RD. And it might have an index A, which I'll denote A, under which is kind of a spin index. So this index describes how this operator transforms under the rotations, under the rotation group. And sometimes I'll say Lorentz transformations instead of rotations. And don't be misled, if I say Lorentz transformations, it might mean Euclidean rotations, or it might mean boosts and everything else. So that's just a common language. So the spin tells us the transformation properties under rotation. And it's an index, generally it's an index in some representation of the group SOD, which is the group of rotations. If you want to work with fermionic operators, spinors, then you need to think about the representations of the corresponding spin group. So the double cover of SOD. Now, in principle, there is no restriction on what this spin index can be, what kind of representation it can transform in. In this lecture, we are mostly going to focus on so-called traceless symmetric representations. And so for us, this A is just going to be a sequence of vector indices. So it's going to be J vector indices, where J is called, I'll call spin. So spin 1 would have 1 index, spin 2 will have 2 indices, and so on. And so the operator, let me write this here, it's going to have mu1, mu_j, and it's going to be symmetric in all these indices. So if you permit these indices around, it doesn't matter. You're going to get the same thing back. And it's also going to be traceless, meaning that if you contract it with the metric, which in our case is going to be the flat metric, but in general, if you contract it as a metric G over any pair of indices, doesn't matter which pair because it's symmetric. So if you contract, for example, over the first pair of indices, you just get 0. That's what traceless means. So this is the simplest kind of representation for this group. If you, well, hopefully that's somewhat familiar. We are going to use so-called index-free notation or representation for this type of operators using a polarization vector. So let me introduce that. So instead of writing this expression OX with all these indices, I will often contract all these indices with a polarization vector. So I'll introduce some vector Z, and I'll contract my operator with J copies of this vector. And this whole thing I'll just denote by, it's a function now of X and of Z. So the point of this is that if you know this function, you can recover the original operator. Specifically, you can just write, say if you want to recover the original tensor, you can just apply derivatives with respect to Z. On this function. And if you divide it by J factorial, you're just going to get this the original tensor back. Yeah. Good question, thank you. So what this achieves is that it kind of uses the fact that this is a symmetric tensor, it's symmetric in these indices, and so because of the fact that it's symmetric, it turns out you can encode it by this polynomial in Z. What this doesn't use is the fact that this is a traceless tensor. So I can simplify this a bit further. Because once we applied this differential operator here, we know that we got a tensor. But also know we're supposed to get a traceless tensor. So we can, at no cost to us, just subtract all the traces. So we can subtract traces. And if I want to be concrete, then one way, so for example, if we had spin 2, then I could say that O mu1 mu2 of x is 1/2 partial z mu1 partial z mu2 O of x z minus 1 over 2d. Let's say if we're in flat space, so my metric is just delta mu 1, mu 2, then just the Laplacian z. So this is what it would mean to subtract a trace in this case. Now, if we did construct our O of x z using this formula, where O is traceless in the first place, then this term would simply be 0. So this term is equal to 0. I can write it or I can not write it, it doesn't matter. But if I do write it, this expression gets a new nice property, which is that this formula, like the left-hand side, is not going to change if I change this O of x z by, say, O of x z plus z squared times something. So where z squared is just z dot z. So if I add this kind of new term to O of x z, this term is going to cancel between these two parts. And so after I have subtracted these traces, in this example here, or in this my general formula here, now this expression, it doesn't care if I modify O of x z by terms proportional to z squared. And because of that, using this expression now to go back, I can treat O of x z to be defined only. I can basically treat these two expressions as equivalent. So I can treat O of x z as being defined modulo expressions proportional to z squared, which is the same, if you think about it, as basically treating z squared as being 0. Now, if you're in Euclidean signature, there are not going to be any real vectors which satisfy z squared equals 0. But we can just, since it's a formal device that we're using, we can take z to be a complex vector. This doesn't matter for us at this point.
So in these dots, they shouldn't be dependent on z, right? Otherwise.
Yeah, so in this example, there shouldn't be dependence on z because it's spin 2. But if I had, say, spin 10, then I could still have a degree 8 polynomial in these dots. And this still would work. I'm just not doing that because subtracting traces in spin 10 is a bit harder. And so you can prove formally in this way that, in fact, you don't need to know the values of this O of x z for all values of z. You just need to know its values on a set of polarization vectors which are null. So and that's enough for you to be able to reconstruct the original traceless symmetric polynomial. So that's how we're going to encode this object. So, traceless symmetric tensor. So instead of working with these tensors, we're going to treat them for, and you can go back and forth, for O of xz. So in here, what this is required to be is a homogeneous polynomial in z of degree j, and understood modulo z squared equals 0. So this set of objects is in one-to-one correspondence with these traceless symmetric tensors. And it's just a bit easier to work with this, as we'll see. Any questions? This is very cool. You should all be very excited. No, I'm kidding. This is just a technical thing. You don't have to think about too much. Just was a good point to make right now. So, but what does it even mean that we have an operator which transforms, which has the spin index and which transforms in some representation of SOD? So to describe that, let's go back for now to kind of a generic index, which might be traceless symmetric, might be more complicated. And let's see how this shows up. Now, I'm saying that this transforms in some representation of SOD. What this means is that suppose for now that we just have a quantum field theory, not necessarily even a conformal field theory. Suppose we have some Poincare transformation. So the Poincare transformation can consist of a SOD rotation, which I'll call R, and some vector C in RD, which denotes a translation. And then what kind of the meaning of all this is that basically that's literally what having this index and this argument means, is that if you apply a unitary transformation to this operator, parameterized by this R and C, so our symmetries are represented by unitary operators. So if we conjugate this operator by the corresponding unitaries, what we'll get is the representation matrix for this representation corresponding to R, except that you need to put an inverse here, acting on OB, and then we have rotation and translation just acting on the argument of O. So local operators just have this property that, if you apply a Poincare transformation to them, so you translate the space and you rotate the space, then the operators get translated and rotated. Their arguments just gets transformed according to the Poincare transformation, and the index gets rotated. Now, when we talk about conformal transformations of these operators, it's going to be just a slight generalization of this formula to conformal symmetries. But what does this mean? How do we use this? Because we said that conformal field theory is defined by local operators and their correlation functions. So in practice, what this means is when we have this notation for a correlation function of a bunch of operators, having a symmetry just means that it's equal to the same correlation function where you replace all your operators by their transformed versions. That's the statement of symmetry in this case. Any questions?
Was the thing that you had on the board before about being able to split it up into the one thing and then the traces, that's only true for traceless symmetric representations? Or is it true for any local operator you can think of?
Traceless symmetric representations are just traces. The tensors there are traces. So if you have irreducible representations, there is no way to split any of them in any way, including traceless symmetric operators. These are reducible representations, and you cannot split a traceless symmetric operator into something in the trace part, because the trace of it is 0. What I was saying here is that simply when I introduce this Z, I start with a traceless symmetric tensor. And one way to think about this is that if I don't introduce the Z squared equals 0 constraint on Z, then I have indeed encoded this tensor in terms of this polynomial of Z. And now I can go back. And when I go back by this formula, if I don't put this here, the only thing that I'm guaranteed is that I'm going to get a symmetric tensor. Not guaranteed that I'm going to get a traceless tensor if I just plug anything here. Which means that the fact that I need to get a traceless tensor is some extra constraint on this polynomial here. What I want is not to have extra constraints. I want to kind of explain very concretely what sort of polynomials I'm allowed to have. What I'm doing instead then is I'm saying, well, I'm just going to subtract whatever traces I might have. And in that case, this new formula guarantees me that I get a traces thing in return, no matter what I put here. But the downside of this is that after I subtracted this, there are now some polynomials that I can put here, which will just give 0 if you apply this formula. And these polynomials, turns out, are precisely those which contain a z-square inside of them. So that's why I'm saying that, okay, now you have a new formula, and you're now allowed to put any polynomial on the right-hand side. And as long as you treat this polynomial's modulo z² equals 0, then you're basically going to be back in one-to-one with trace symmetric tensors. There was so this subtraction of traces only appears for this formula. It doesn't. You cannot subtract traces from a traces symmetric thing because it's already traceless. All right. So when we go to conformal transformations, this formula just needs to be generalized slightly. So conformal transformations we can parameterize by well, Poincare transformations are easy to parameterize by a rotation and a translation. For conformal transformations, such parameterizations are not particularly useful. So instead, what we do is we just say, okay, conformal transformation is going to be a map from, say, RD to RD. It's a conformal map. As we'll discuss, this is not very accurate. You have to write SD here and SD here, but we'll come back to this later. So let's just close our eyes and pretend that this makes sense. Then the formula is basically the same. So now we have the unitary transformation parameterized by phi. The conformal transformation needs to act on the argument here. And before what I just erased, the Poincare transformation simply acted on x. So now we just simply act as phi on x. The only thing that needs to change is this sort of prefactor, because we don't have r anymore, and we also now have the scaling aspect that wasn't here previously. So it turns out that what we need to do is simply to put here some new factor omega of x to the power delta, make r depend on x, and define now what this omega and r are. And they're defined by saying that omega of x, let me write it over there, it's a bit low. So omega of x times r mu of x is just equal to partial phi mu partial x nu of x, and the constraint is that R is an orthogonal matrix. So the point here is that if phi is a conformal transformation, then this matrix of partial derivatives is guaranteed to be an orthogonal matrix, a rotation, up to a scale, because the locally conformal transformations can rotate, but also rescale. So here we are splitting this kind of infinitesimal version of phi. So formally we would call this the differential of phi. We are splitting it into a rotation and a rescaling. So omega describes the rescaling, r describes the rotation. And then we make here the rotation act by some matrix appropriate for our representation, and we make the rescaling act by just an overall factor, and this number that appears here is called the scaling dimension. Any questions?
Why is just a conformal transformation on manifold M and not straight to the
Sorry?
The phi should be both from manifold M to manifold M. So
Well, this is in the case when M is RD.
okay, not restricted to the flat space.
Yeah, so now I'm restricting to the flat space. In principle, you could put a manifold here, but then you would have to be a bit more careful with what A means, because in a general manifold you would have to talk about some vector bundles, and that all would have to be valid in a vector bundle. I mean, here it's also valid in a vector bundle, but everything is just trivial over RD, so I don't have to say these words. Other questions? Yeah.
There you provided only a single equation to read of omega and R. Is it unique? Like I can uniquely identify what is omega and R from this single equation?
Well, maybe you need to also ask that omega is positive, and then it's unique.
Okay.
You don't believe me?
I'm not fully convinced, because can I include some part of scaling in the R and no?
No, no.
Maybe the rotation matrix has some properties that is that.
So if you call this matrix A, then what you can prove is that A transpose A has to be some constant, which in this case is omega squared times identity matrix.
Okay.
So you can read off omega here is the square root of this constant in front of the identity matrix. And if omega is positive, this fixes it uniquely. All right. So, however, what I should stress is that here, when I wrote this rule, this only applies to operators which we call primaries. And if your operator transforms under conformal transformations, like so, then it's called a primary operator. And if it doesn't, then it's not called a primary operator. Fortunately, in unitary conformal field theories, all operators are either primaries or derivatives of primaries. So any operator is going to transform in this way, or is going to be a derivative. By derivative, I just mean that you have of, say, OA of x. Then, of course, you can apply partial, say, partial derivative with respect to x mu. That's going to be a new local operator. You can apply as many derivatives as you want. So any local operator can be written as a linear combination of primaries and derivatives of these primaries. That's true in unitary CFTs. In non-unitary CFTs, this might not necessarily be true. And because a lot of properties, I mean, basically all the properties of the derivatives of primary operators follow from the properties of primary operators. For example, if you know the correlation function of the primary operator, you can compute the correlation function of its derivatives by just taking derivatives of the correlation function of the primary. Because of this fact, basically most of the time we only talk about primary operators and we don't separately talk about the derivatives. And the derivatives are also called descendants. So with that in mind, let's briefly review how the correlation functions of primary operators look like in CFTs, and then we'll go for a break probably. So the correlation functions are expressions of this form. What they mean technically is basically, so one way of explaining what the correlation function is to imagine that your CFT is described by some sort of path integral. Maybe you have a path integral or some field phi, and you have some action S of phi. And if you just do this path integral, then we're going to get something that's called the the partition function z. Another thing that we can do is, for example, do the same integral, but with phi maybe of x inserted here. And if we divide this by z, then this is what we would call the correlation function involving just phi of x alone. I could also add phi of y, in which case we would call this, we would denote this phi of y. Of course, phi is not the only local expression you can write in this sort of theories. So for example, you could write phi squared. And then this would be a correlation function involving a different local operator, which is called phi squared. Now, of course, if you've seen this before, you would know that you have to be careful when writing things like phi squared, but after some appropriate care, you can make sense of this expression, and then you can make sense of this correlation function. So in this example, most likely, depending on your theory, phi will be a primary and phi squared will be a primary, but something like partial mu phi is not going to be a primary. And so the correlation functions, we call them 1-point function or 2-point function. So this would be a 2-point function because it has 2 points, x and y. Over there I have an example of n-point function. So with this in mind, if we just again abstract and think about the general CFT and look at 1-point functions, then it's a simple exercise to check that, simple exercise to check that conformal invariance of correlation functions requires that all 1-point functions vanish, well, that this 1-point function vanishes unless so the spin is trivial, so the spin is 0, so the index A is basically not here, and the scaling dimension also vanishes. So unless O has scaling dimension which is 0 and spin which is also 0, the 1-point function has to vanish. Now the standard assumption is that the only operator with scaling dimension 0 and spin 0 is the so-called identity operator. And the identity operator is basically, in this language, just inserting a constant 1 here inside of the integral. And so the only 1-point function which is non-zero in this generic CFT is the 1-point function of the identity operator, and that's just equal to 1. Because if you insert 1 here, then you get back the partition function. It cancels, you get 1. Now, when you look at 2-point functions, OA1, x1, O2, A2 of x2, then again you can prove that this is 0 unless two things hold. So first, delta 1, scaling dimension of operator delta 1 is equal to scaling dimension of second operator delta 2, and secondly, the spin representation of these two guys have to agree. So I'll denote the spin representation by rho. So rho 1 has to be so-called conjugate reflected representation of rho 2. So you take the dual representation and then you reflect it, and for the current discussion you can think of reflection as just flipping. If you have some sort of left-handed representation, you replace it by right-handed representation. For trace symmetric representations, this means that just the spin of the first is equal to the spin of the second. But for general representations, the condition is this. And from this statement, what you can show is that in unitary CFTs, it's always possible to find a basis of local operators, local primary operators. I'm talking about primaries here. It's always possible to find a basis of primary operators so that the two-point functions are only non-zero between an operator and its Hermitian conjugate. So conventionally, we say that the two-point function O1 and O2 is non-zero unless O2 is just O1 Hermitian conjugate. So we agree to use a basis of operators where this holds. And so the two-point functions are so-called diagonal in unitary CFTs by convention. Any questions? Okay. So I'm sorry I'm going fast, like in case, I'm sure this is a very awkward lecture because for those of you who are familiar with this is all extremely boring. I do hope that you didn't everyone know that, but for those of you who are familiar, it's extremely boring. And for those who aren't familiar, this is probably way too fast. But that's such is life. So hopefully we'll put everybody in the same position in a little bit. Let's just discuss three-point functions very quickly. So when we're considering three-point functions, and a bit later I'll give explicit examples for this. I should say that not only for the two-point functions, not only can you show that they have to vanish unless these conditions are met, also when these conditions are met, you can show that there is a unique form allowed for this two-point function by the conformal symmetry. So up to overall normalization, there is a unique expression you can write for this two-point function. And by convention, by choosing normalization of these operators appropriately, you can just make that two-point function to equal to some conventional expression whenever it's non-zero. And so in this sense, there is no information contained, and no physical information contained in these two-point functions. But then there is a physical information contained in three-point functions, because you have already chosen a basis of of primary operators, made sure that the two-point functions normalized as you like, and now you don't have any freedom to do anything. And when you look at three-point functions, it turns out that they're generically non-zero up to some selection rules which are more complicated to describe. And if you solve the constraints of conformal invariance for these three-point functions, what you find is that if you look at three generic operators, the solution takes the form sum over some index, so some finite sum over the number of terms in the sum that depends on the specific Lorentz or spin representations of these primary operators. And then you have some undetermined constants lambda I multiplying something I'll denote q. So if they depend on x1, x2, x3, and they have indices a1, a2, a3, so this q is going to have all these indices. And depend on all these coordinates. So all the index dependence and coordinate dependence goes into Q, and there is a finite dimensional space of Q's that you can find, and so you find some basis, and any element of this basis can appear as arbitrary coefficient. These coefficients are determined by the theory. So this is theory, specific CFT. It's kind of concrete CFT data. This is just symmetry. It's determined by symmetries. And again, we'll see explicit expressions later on. And then when you go to 4-point functions, then situation becomes more complicated because 4-point functions, the expressions are the same. So you have some finite sum, have some basis of kind of invariant objects, but these lambdas, in case of 4-point functions and higher, can now depend on the coordinates themselves, but they only depend on so-called conformal cross ratios, and we'll get there when we need it. So, any questions at this point? Welcome back. Let's continue. Yeah.
Because you said we can think of the CFT as defined by operators and the correlation functions. So is it true that for any chosen set of lambda I, we can think of there exists CFT will produce this correlation function? Is there any further restrictions?
Yeah, there's further restrictions. So these, in principle, these numbers and these deltas and these lambdas are everything that you need to know. So if you're only interested in correlation functions of local operators, then it turns out you can compute all of them, not just 2-point functions and 3-point functions. You can compute all of them using this information. But not any set of lambdas and deltas will give a consistent way. So for example, the reason is that, say, the 3-point functions are just given by this. Then there are 4-point functions. Turns out you can compute 4-point function using these lambdas. But there are several ways of doing the calculation. They all have to give the same answer. If you just pick different lambdas, just pick some random lambdas, then there are 3 different ways of doing the calculation. 3 different ways will give 3 different answers. But you need the answers to match magically. So these numbers, they need to satisfy a condition called crossing equation. You can watch Andy's lectures about that. I think they were precise about this. The sums have to satisfy some equations called crossing equations, which make sure that these computations will always agree when you compute higher point functions. And these are very constraining equations, so it's very hard to find a set of lambdas which works.
In practice, how we find all the primary operators?
Well, there are infinitely many of them, so it will take a long time to find all of them. But in a given theory, you can just say if you have a free scalar, free massless scalar, then you have this field phi, and you can start forming like phi. You can form phi squared, or you can take phi times some derivative of phi, combine them in various ways. So most of the expressions that you will write will not be primary, but then there is in principle a systematic way of predicting how many primaries of particular form you should get, and then you need to solve some kind of linear equations to find out which of them are primary. You can understand how they transform these expressions, then you just need to find those which transform in this way. In principle, it's a little bit of a non-trivial task to write the precise expression for a primary. It can get nasty, but there are tricks that you can use. Other questions? All right. So, let's see where we're at. So let's discuss now, finally, what's the key difference between Lorentzian and Euclidean signature, and what are the different relations. So now, for this discussion, you can forget more or less everything I said about primaries and conformal symmetry. The discussion we're going to have now is exactly the same in conformal field theory and also in general quantum field theory. So we're going to discuss applies to all quantum field theories. So raise your hand if you studied quantum field theory. Okay. Now, those who studied quantum field theory, so you know quantum field theory is supposed to have Hilbert space. It's like quantum mechanics, there's Hilbert space in quantum mechanics. So quantum field theory is a fancy quantum mechanics, so it has a Hilbert space. And let's run a sociological experiment. Can someone give me an example of a state in quantum field theory? So you have your favorite, let's say I have QCD or something, your favorite quantum field theory. Can you give me an example of a state in the Hilbert space? Vacuum state, great. All right, so I'll denote it like so. This is going to be the vacuum state. Okay, now can you give me an example of a state which isn't a vacuum state?
One proton.
Huh?
The one proton state.
One proton state, good. Well, you need to specify that the proton is flying somewhere, but yeah, you can specify. There are states which we call one particle states, which have which have, say, one particle with particular momentum and so on. But if, let's say, you didn't know if the theory has any particles or what these particles are, could you still make? Let's say we had let's suppose our theory is this scalar, some sort of scalar quantum field theory that I mentioned before. Something like this. So, okay, that's fine. What I'm trying to get at is that you can take, vacuum state and you can act as various operators in the vacuum state, you'll get other states. So one operator, for example, in such theories, which we have a scalar field, is just phi of x. So you can act with phi of x on the vacuum, you'll get another state. You can also act with, say, phi of x, phi of y. And get another state. Turns out these are actually not states, so we'll discuss why they're not states. If you're being super careful, they aren't nice states yet. But for now, we'll pretend that they are. And if you can have these things, you have states and you have inner product. So you can form inner products between states. So we can compute what we call the vacuum expectation values. So let's say if we have this field phi, we can just insert a bunch of them, compute the vacuum expectation value of this product of phi's. More generally, if we were to consider not necessarily phi, but we could, act here with phi squared or something more complicated, we can just consider the same sort of expressions, but for products of local operators. So you can have vacuum expectation values of products of local operators. And these are different from these expressions that I was writing before. So before I was writing these correlation functions. Which were computed by these path integrals with this, let's say we had some action. So before we had these correlation functions, which are computed by path integrals with some insertions of these operators normalized by the partition function. Now I'm discussing vacuum expectation values, and for one they have different notation. But it also turns out that while these make sense both in Lorentzian and Euclidean signature, these only make sense, strictly speaking, in Lorentzian signature. There is a reason why when you open lecture notes or textbook on Euclidean CFTs, you don't see a lot of this. You just see these things. Sometimes you'll see radial ordered products or time ordered products. And so you might know that these are these guys are versions of this for particular ordering of the operators in the expectation value. So sometimes you can see that people will tell you that, and this is true, that this is, say, a time-ordered product of these things. Well, what does time ordering means? What does time ordering mean? It means that if you want to compute this expression, you are to look at the list of the local operators that you have here. You have different x's. You have some sort of notion of time. You have to look at the time part of every one of this xi, and then you have to order these operators so that the time increases that way. So the time grows in that direction. And then once you order them in this time-ordered fashion, then you can compute the vacuum expectation value. So for some reason, when we're work in Euclidean signature, we only talk about time-ordered products. So sometimes you can encounter radial-ordered products, but this is the same as time-ordered, just where your time runs radially instead of in one direction. Conceptually, they're the same thing. So why is that? Why do we care about time-ordered in Euclidean and we don't discuss these ones? So first, let's discuss briefly why do you get time-ordered from this path integral. Whoop. Raise your hand if you know that path integral computes time-ordered correlators, if this sounds familiar to you. Okay, actually a fair amount of people have seen this, but let me just remind you very quickly why this is the case. So if we choose some direction of time, let's say this is our space, and we choose some direction of time, in Euclidean signature it can run radially in a CFT, or it can just run like this. So you have some time slices. And then if we insert some number of operators at points, I don't know, x3, x1, x2, x4, then and we want to compute a path integral maybe with insertions of phi of x1, phi of x4. So we have a phi sitting at all these points. So if we want to compute this path integral, we can just cut it up by time slices. Then say on this time slice, we are performing path integral everywhere below. And that gives us the vacuum state. Then we act on this vacuum state with phi at x3 once we go up to here. Then we again compute path integral here. This gives us some time evolution. We act with phi at x1, then we evolve again, act with phi at x2, evolve, act with phi at x4. And what this ends up being is that by slicing up our path integral, we find that we are computing this sort of expectation value. So this first vacuum comes by doing path integral over this half space below. This vacuum comes from doing the path integral over this half space above. And then these guys just come by progressively doing the path integral. And the order is determined by that. And this is clearly just the time order of all of these points. So path integrals compute these time ordered things. Now what would happen if you tried to compute a non-time ordered object like so in Euclidean signature? So for this, for now, I will only write time arguments. So we'll think that we are in Euclidean space. There's Euclidean time direction running upwards. Or it could be the radial coordinate, if you want to work in radial quantization. And so we have some operators. We can just take phi for now to correspond to this example. So we have phi of t, and in terms of kind of evolution is given by e to the minus ht in Euclidean signature. So in Lorentzian signature, kind of in real time, you would have e to the minus I ht, but when we're in Euclidean, time evolution just goes e to the minus ht. And phi of t can be expressed like so. So h is the Hamiltonian. It says that if you want to act with phi at time t, you can just evolve for time t, act with phi at 0, and then evolve back. And then suppose we use this to compute something of this sort. So we have phi of t1, phi of tn. And we just plug in this expression. We use the fact that h acting in vacuum gives 0, because it's the vacuum state. And then we find phi of 0 e to the minus h t1 minus t2 phi of 0 e to the minus h tn minus 1 minus tn phi of 0 0. So by just taking this product, using this formula, and plugging it in, we get this expression. And here, again, I'm only writing down the time argument. The positions in space can be anywhere you want. And to see what the problem with this is, let me just write it maybe in the case of two-point function, because it's already enough to see what's going on. So for a two-point function, we'll just get 0, phi of 0, e to the minus h t1 minus t2, phi of 0. So to compute this, let's insert a complete set of states of Hamiltonian eigenstates. So I'm summing over some n, and I have, so this, this is some kind of generalized sum. In practice, it will be an integral. T1 minus T2. And the problem here is that this expression, it will depend on n, but it will not decay in any nice way at large energies. It will typically behave, and you can do this as an exercise maybe in the free theory. This part of the expression will just behave with some power of the energy En of the state n. Whereas this is an exponential. So when T1 is greater than T2, this exponential is nicely suppressed at large energies, and this perfectly converges. But if T1 is less than T2, then we have an exponentially divergent factor here. At large energies, this is going to be very large. Even if this decays, it's not going to decay quickly enough to cure this exponential divergence. And so this expectation value, therefore, is only finite when T1 is greater than T2. Similarly here, this expectation value, this ordered product, is going to be infinity unless here all the parentheses are positive, so that we have Hamiltonian multiplied by negative numbers. So unless T1 is greater than T2, which is greater than T3, greater than Tn. So while technically, the conclusion is that while technically you can write such things without using the time-ordered symbol, without insisting on time ordering, in Euclidean signature they don't make sense unless the times are actually ordered. And so the reason why we care about this time ordered, or things computed by path integrals in Euclidean signature, is because these are the only correlation functions you can basically compute. And turns out that once you go to Lorentzian signature, then Lorentzian signature, all other orderings also start making sense. And the reason for this is that in Lorentzian signature, we have this evolution operator instead of this one. And so if I'm to repeat this exercise, I need to put I everywhere. And when I put an I everywhere, what I find is that there is no problem with exponential divergence. It doesn't, or at least, whether there is a problem or not, it doesn't matter whether it's T1 greater than T2 or T1 less than T2, it's just going to be the same oscillatory factor. You can still ask, of course, whether this oscillatory factor is good enough. And it turns out that sometimes it is good enough, sometimes it isn't good enough. To make it always work out, what we have to do, usually, is the following trick. So to clarify again, what happens in Lorentzian signature when we have real-time evolution with a factor of I here is that this may grow as a power law, it might decay as a power law, it doesn't matter. This just oscillates. It oscillates irrespective of the ordering of the times. So all the orderings are equally good or bad. Now I just want to make a comment about how to make sure that this sum actually makes sense. And to make sure that it makes sense, all you need to do is to multiply it by some function of T1, by some function of T2, and integrate over T1 and T2. And the reason is that if you integrate, if you compute this integral, f1 of T1, f2 of T2, e to the minus I e T1 minus T2, you're basically taking a Fourier transform of these functions f1 and f2. And specifically, this is just equal to the Fourier transform of x e function 1 times Fourier transform of function 2 minus e. And so if you choose your functions f1 and f2 to be very nice, like smooth and quickly decaying, then their Fourier transforms are also going to be smooth and quickly decaying. And once you integrate in this expression, you're replacing this factor by these Fourier transforms, which are smooth and quickly decaying. And so it's easy to compute the sum because there is no problem at high energies now, because by integrating against the so-called test functions, you made sure that each term in the sum now actually goes to 0 very quickly as energy goes to infinity. So it turns out that in general you need to do this trick. You need to, you need to smear in time against some test functions, and then you will definitely get numbers. And so the conclusion of all of this is that this expression, this sort of expectation values, they don't make sense at all unless the times are ordered in Euclidean signature. But if they are ordered correctly, then they actually make very good sense because you have an exponentially decaying factor. On the other hand, in Lorentzian signature, you don't have to worry about the times being ordered. But in practice, you do have to worry about smearing this expression with some test functions to make sure that it's finite. And when you have some function that doesn't maybe necessarily make sense point by point, but if you multiply it by another function integrate, then it makes sense. We say that this function is not actually a function, it's a distribution. So technically these are called distributions, and the standard name for them are Wightman distributions. Well, the more common name is Wightman functions, but it's a little bit of a misnomer because they are not really functions, they're distributions. And by the virtue of being distributions, by the way, they also make sense when the points coincide, when you have operators inserted at the same point. Well, they make sense as in like delta function makes sense at x equals 0 in the same way. So, sorry, there's T, Wightman. Any questions at this point?
So, in Lorentzian spacetime, now you have more than just time order correlators. So, do you think like we have more observables or something, more informations are encoded in Lorentzian spacetime which cannot be derived from Euclidean or something like that?
So, as we'll discuss, you can determine all this. So if you know the Euclidean correlators by node decontinuation, you can obtain all these Wightman distributions. But the way this is done is by node decontinuation, which is in principle an ill-posed problem. If you only have an approximation to Euclidean correlators, then you might not necessarily be able to understand what is the node decontinuation, because terms which are very small can become very large after a node decontinuation. So even if you had a small error, the error can become very large after node decontinuation. So it can be hard in that sense, but in principle, you can node decontinue. That said, you can just ask some physical questions, and to some of these questions, the direct answer will not be a time-ordered correlator, but will be this correlator. It's sometimes called the out-of-time ordered correlator, which is a weird name because you first invent time ordering, then you work with time-ordered correlators for a long time, and then you realize that you want to work with something that's not time-ordered, and you call it out-of-time ordered. But that's a name. So when people study things like chaos in various situations, they like to consider out-of-time ordered correlation functions. Any other questions? Yeah.
If you work in Lorentzian signature, but you restrict yourself to only talk about time-ordered expectation values, do you still need to do this smearing in time, or you are guaranteed that they all make sense?
You still have to smear in time in principle. I mean, so in some theories maybe not, but like as far as you can prove things, you have to still smear in time. There are some kinematical configurations in which you can prove that this. So one comment is that time-ordered correlator in any configuration is equal to one of these Wightman functions, because you just order the operators appropriately, and then the value is equal to that Wightman function. And so if you have to smear Wightman functions, then you also have to smear these time-ordered correlators. Now this overlooks the problem of coincident points. So the Wightman functions are defined as distributions unambiguously at coincident points, whereas time-ordered correlators aren't. And so sometimes, when I say that you have to smear Wightman functions, sometimes you just have to smear them in the sense that they contain information at coincident points, and you might need this information. But there are also some regions, some kinematical configurations which don't have any coincident points, for which we cannot prove that you do not need to smear. You might or might not need to smear. Then there are some configurations for which we can prove that you definitely do not need to smear. It's just going to be a smooth function. It's a bit of a technical question, to be honest. Yeah. Other questions? All right, let's quickly discuss what's the relationship between these different. How do you go between, say, time? If you know the time-ordered correlator, how can you compute the Wightman functions and so on? So the difference between Euclidean and Lorentzian signature is basically in this factor of I. So if I introduce sort of Euclidean and Lorentzian time, then the identification is that e to the minus h time Euclidean should be the same as e to the minus I h time Lorentzian. And which means that Euclidean time is I times time Lorentzian. And this is the idea of kind of Wick rotation. Wick rotation just says, oh, let's replace time by this. But this is, of course, very informal. Nevertheless, from these expressions, you can prove a formal way of relating and a rigorous way of relating Wightman distributions to time-ordered correlators in Euclidean signature. Because remember that here, the difference between the Euclidean correlator and the Lorentzian correlator was in this factor of I. So suppose you know the time-ordered correlator. So suppose you know O1 of T1 or N of Tn. So, and I'm going to call this T Euclidean 1, T Euclidean n. And suppose, so we just know this. So let's order T, let's choose some values for this Euclidean times which are ordered. Sorry, the other way around. So let's choose the values that are ordered. And then we can use this expression that we had here without this orange I to say that, okay, this is equal to 1 of 0 e to the minus h time Euclidean 1 minus time Euclidean 2 over 2 of 0, and so on. And as long as I keep this factor here positive, this makes sense. And everything, so all this sort of sums, like here, converge perfectly. There is no issue. One thing you might notice is that it's not necessary for me to make sure that this number is real. All I need to make sure is that its real part is positive. So what I need is not for this expression here to be real, but just that its real part is greater than 0. But then I can do the following. I can start analytically continuing in this T1 and T2 to give them imaginary parts. So not changing the real parts, just to start giving them imaginary parts so as to reproduce these factors. So I can start adding here to time Euclidean. I can start adding here plus I time Lorentzian 1 plus minus I times Lorentzian 2. And that's not going to break my expression in any way. That's going to be all nice and smooth and analytic. So I can just add these terms here by analytic continuation. I'll just start moving in this imaginary direction. And then once I'm there, I can take the limit of the Euclidean times going to 0 whilst preserving the condition that they are ordered. And if I do that, I'll end up with this expression without ever encountering any sort of singularities. And so what this tells you is that you can analytically continue from Euclidean time-ordered correlators to Lorentzian Wightman distributions by the following recipe. You first order the Euclidean times in a way in which you want the operators to be ordered in the end. So for example, here I wanted the operators to be ordered from 1 to n. But maybe, maybe instead I wanted to, so I have here some O2. And maybe I didn't want the Wightman correlator that I get to be O1, O2. Maybe I wanted it to be O2, O1, right? If I wanted it to be O2, O1, then here I would still, of course, start with the time-ordered correlator of this form, because in the time-ordered correlator, the order doesn't matter. But when I choose the Euclidean times, I would reverse these two guys. I would put second time to be the largest and the first time to be the second largest. And then when I time order, I would have to put O2 first and then O1. So whatever order I might want, I order my Euclidean times in the same way, which makes the time-ordered correlator equal to this expression. And then once I've done that, I start analytically continuing. And I analytically continue by first adding imaginary parts to my Euclidean times to make sure that I reproduce the kind of Lorentzian part. And then I send all the Euclidean times to 0 while preserving their order. And in this limit, I'm going to get the desired Wightman correlator. And in this way, it's possible to obtain any ordering. And similarly, you can also go back from any Wightman correlator to the Euclidean correlator by just reverse of this analytic continuation, which also means that you can go from any Wightman ordering to any other Wightman ordering by analytic continuation, basically through going through this Euclidean point first. So I think we should maybe stop here. Perhaps we have a couple of minutes if there are any questions.
So how do you implement it in path integral?
I'm not saying that you're supposed to implement it in path integral. I'm saying that if you know the correlation function, so for example, CFT is a good playground because you have explicit expressions, say, for 2-point functions or 3-point functions. If you know it exactly, then these statements are true, that there is this domain of analyticity, and if you go through it, various limits will lead you to Euclidean correlators or to Wightman correlators. I'm not saying that this gives you an obvious way of how to explain how to do like path integral between Lorentzian and Euclidean. That does.
No, we just figure out that time ordered we cannot do as path integral, right? Now you say.
Well, time ordered is what the path integral does.
Yes, exactly. So
yeah.
Now you say we can just go from one to another side of one. Okay, makes sense.
So you can still compute out of time-ordered correlators using path integrals, using Schwinger-Keldysh contours, but it's not the same. I mean, I guess you can sort of motivate Schwinger-Keldysh contours in this way, but but it's not. I don't think you can derive Schwinger-Keldysh contours in this way, but you derive them in another way. That's other questions? Okay. The torture is over.